All right, so what we're going to be doing today is talking about these things called slope fields. If you were in Create-P pre-cal last year, you actually got at least part of slope fields, not everything, but you already kind of know, well, what a slope field is. For everybody else, though, I'm going to teach it as if you've never seen this before. But just know if you were in Create-P last year, this should look familiar. Okay, so basically, what is a slope field? It basically is a field with lots of little slopes. Okay, so if you look at this is a calculator screenshot, and this is from a graphing program. At every coordinate, at every like the point 1, 1, 2, 1, and so on, there's a little segment of a line that has a slope that represents the derivative of the function, or it doesn't have to be a function, but derivative at that point. And so if you look at this one, I'm not going to talk too much about what these are, but if you kind of follow, yeah, it kind of looks like sinusoidal, doesn't it? All right, and so all of these little segments, okay, together as a slope field, they represent the derivative of sine, which is cosine. Okay, so this one over here, what do you think this one is? Yeah, probably a cubic of some sort. All right, and so we could, these derivatives then would represent the derivative of a cube, which would be what type of function?
Quadratic.
Yeah, so this differential equation would be quadratic here. Okay, so that's about as much as I want to go into it, except to say that, I just picked a certain point. I could have picked a point up here, and then if I followed these little segments, this would move the whole thing up. It's not really changing the shape, but it's moving it up. This is what the plus C is all about when we integrate. Graphically, this is what plus C does. It moves the graph up or down. Okay, so we've seen algebraically what it does. This is what it does graphically. Okay, we're going to start calling this an initial condition. And so if we look down here, and it says you may be asked to construct a slope field and given an initial condition. All right, and so dy over dx equals x minus y. This is a differential equation. This is representing the derivative of something. Okay, and we can construct the slope field. Now on the next page we're going to do this by hand, but on this one we're going to go ahead and do it in the calculator. I'm going to show you how to do that. And then this initial condition is going to allow us to construct the actual curve. All right, and so all the directions are going to be right here on your paper. I'm going to show you up here. So the first thing we need to do is go to mode. Oops. If you go to mode and see where it says graph function, and it says right, if you get right, there's a drop-down menu, and we don't want to be in function mode. We want to be in differential equations mode. Okay. And so now we want to go to y equals. And it should look like this. And y equals, is right up here, depending on whether you have 89 or 89 titanium, the colors are different, but, you can figure that out on your calculator, just color code it. So if yours doesn't look like this, that's because you didn't save that new mode, okay? You got to press enter 2 times, basically. All right, and so y1, and this stands for derivative. If we want to do the derivative of x minus y, first of all, we need to recognize that this calculator is going to use t instead of x. So this is something we need to note here, okay? And so if we want to do x minus, we really need to do t, and t is right here, t minus. And the y, we can't just pick y, we got to do y1, which means just type in the letter 1. And so it shows you what to do right here. So y1 prime would be t minus y1. And so you've got to know how to type it in right or it won't do it. Okay, so now let's graph it. So let's graph. Graph is right up here above F3, so diamond F3. Now your window may be different than mine, but you should get a slope field. Okay, if you're not, you're probably just typing it in wrong. All right, we're not going to do a whole lot of this on the calculator. I'm really just showing this to you first because you may want to be checking your work as you go when we start to do this by hand. Okay, so this is the slope field, and you may or may not know what this is supposed to graph. Okay, we'll get to that part. If we want to do the initial condition, it says, minimize this. So we want to do the initial condition of -5. This means the point 0, -5 is going to be a part of my graph. This has to do with plus c, it's the y-intercept, these things are all connected. The way we enter this into the calculator is we go back to y equals, and under yi1, think of I as initial condition, we're going to do the -5, and then I'm just going to graph it again. Okay, so diamond F3, and yours, again, if your window is different, yours is going to look a little different than mine, but it's all part of the same graph. And so you could kind of make a guess as to what you think this is. You could say, oh, that may look like a rational, it may look like a natural log or log, it may look like a root of some sort. Okay, so we're not really sure yet, and that's okay. That's really not the point of this. All right, now the only thing I want to say is that if you're going to use this calculator to graph like normal graphing, you got to go back to function mode. Okay, and so if you're not using this 89 for any other things, then just leave it in differential equations mode for now, and then and then change it later because we're going to be doing slope fields for a few days. But just know that that's how you go back. It's through the mode. Okay, so now let's think about how would we do this without the calculator. And if you want to, when I'm doing this, if you want to follow along with your calculator, that's totally fine, and then you'll kind of see what happens. I would encourage you to at least try it by hand first, because this is what you're going to have to be able to do. And so we've seen things that look like this, and we've gotten answers that look like this. dy over dx equals -x over y. Because the x's and the y's are together, this is telling you that this is probably an implicit differentiation problem, where, we had the dy over dx and then we had to get it by itself and all that. Okay, so they're giving that to us first, and all we got to do to construct the slope field is just do a few little calculations. Okay, so I'm going to encourage you to make a chart like this. All right, so I'm going to pick 0, 1. 0, 1 would be this point right here. Okay? And so the way I know what should be the slope is by plugging it in. -0 over 1 is 0. Can we kind of do, if I change the y, will that change my answer here?
No.
No.
Unless it's
So,
0.
in fact, you're right. 0, 0 is, we're going to save that to the end, because 0 over 0 is a whole, it's in its own category. So 0 over anything else is going to be 0. The negative doesn't affect that. So what this means is that anytime x equals 0, the little slope should be 0. And what type of lines have 0 slope?
Horizontal.
Horizontal. Noticing this pattern is going to save you a lot of work, because there's almost 50 dots right here. Okay? Do you want to be doing 50 calculations? Probably not. So anytime x is 0, so we're going to draw little lines like this. And this means that if, as we go on, I'm going to say this over and over. This means that if my curve is going through the point 0,2 or 0,3 or wherever, it's really, really flat, if not completely flat, right there. Okay, that's what that means. It's the slope at that little tiny segment. All right, do you see another pattern that's kind of similar to this? So I asked if x is always 0, you know what the slope is going to be. Is there a similar pattern? Yeah, if y is 0, it doesn't even matter what x is. If y is 0, then we've got an undefined slope, which is what type of line? Vertical. So that means all these are little vertical lines. So again, I left 0, 0 blank because if you put a horizontal or a vertical here, that would be okay. It's really not going to mess up the total picture, but I'm just going to leave it blank because we're probably not going to need it. Now, you may already think you know what this picture is going to be, so let's keep on going. So now I'm going to do the point 1, 1. It would be this point right here. So -1 over 1, is -1. Now, a slope of 1 is like a perfectly diagonal line, a 45-degree angle, if you want to think of it like this. And negative means you would just go, decreasing that. Okay, think of it this way. Remember, these are coordinates. So sometimes you might want to write it this way if you kind of get lost in the middle of the problem, if you're not sure what you're doing. Are there any other points that are going to have a slope of -1? Yeah, what? Huh?
The whole thing in
Negative
that
one
row.
what?
Whole thing in the column.
Okay, so I heard -1, 1. I'm just picking that out. That's not what, y'all all said different things. So I'm going to pick -1 out, and let's test it to see what it is, right? So -1 over 1 would actually be +1. Okay, so you don't say it's definitely going to be the same on the columns. What are you thinking?
Anytime the y and the x are the same.
Ooh, anytime the x and the y are the same. So like 2, 2, we're going back here, by the way, to when is the slope -1. Anytime the x and the y are the same. So all of those and all of these. Noticing these patterns really cuts down the amount of work you have to do. You could just do 40-something calculations. All right. Likewise, though, the -1, anytime the x and y are negatives of each other, one's negative, one's positive, that's going to give me a slope of +1. Anybody think they know what picture this is going to make? And it is going to make a circle. And that's going to become more obvious as we fill in this slope field. Okay, so let's pick another just random point. Okay, 1, 3. So 1, 3 is going to become -1 over 3, or -1/3. So anytime you get like a half or a third, just think the smaller the number, the flatter it is. So that should be pretty flat and negative. Okay, if we pick something like -2, 1, which would be this point over here, that's going to be -2, +2 over 1, +2. So -2, 1, that's going to be twice as steep as the parent function, so pretty steep. And the larger that number is, the steeper it is. Okay, so I'm going to give you guys a little bit of time to practice. Okay, I'm going to say all the girls, you get quadrants 1 and 4, and the boys, you get quadrants 2 and 3. So just try to fill in the slope field as much as you can. And go through and do the coordinates if you need to. You might pick up on some patterns. I'd say you try, that's great. Okay, so go ahead and check what you've done with what I've done. Okay, you might not have gotten as far as I got. I don't expect that. But whatever you did do should look what I have. And go ahead and fill in the rest. Now on the AP test, you won't have to do this many points. Okay, it won't be like that. If this, it would be either more like matching, or it would just really be cut down to like usually maybe at most 12, points. So just if that puts your mind at ease at all. We just have a lot right here, so we can really get a feel for what we're doing. Okay, are there any questions about how you come up with the slope, like how you fill out the table, or then how do you put it on the graph? What? Mm-hmm. And you just need to do that for every point. And the more we do this, the more you're going to recognize patterns. And sometimes the patterns are more obvious than others. So we're just going to keep practicing this enough, and it'll get quicker, or you'll get quicker at it. This is a lengthy one, but again, we did this first so that you have to do a lot of like.
mean, it just like goes up in incline. It just follows the pattern as it goes around.
Yeah, so like if we were to continue to go out, you'd know this would just get steeper and steeper and steeper and steeper, right? And so you guys were right. This is a circle. And A says sketch the solution curve through the point 0, 1. So I know at this it should be completely horizontal, like a max or a min, in this case a max. And if this is a circle, then really it's going to look something like this. Okay, what's the radius of this circle? 1. Okay, so does anybody remember the equation for a circle? Yeah. Now we're going to come up with this here in just a minute. Algebraically, we're going to come up with this. And really, just for everybody's sake, it's 1 squared, which is still 1, but it's the radius squared. That's the in general. Okay, so I'm going to show you algebraically how to come up with this from the dy over dx statement. Because next time it's not going to be obvious, especially when we get into really weird curves and everything. Okay, what about the solution curve through the point 0, negative 1? Would that solution curve be different? No, it would be the same, right? That can happen, especially with the circle with lots of symmetry. Okay, so the next two then are fairly obvious. Could this be a slope field for y equals 1 over x? No. Could it be a square root of x? No. If you know your parent functions, this is easy. Could this be a slope field for this equation? Now, don't get hung up on the 2.
The radius
Okay.
is 2.
Well, here the radius would have to be square root of 2. But you're right. It would be a different initial condition. But the x squared plus y squared gives me the right shape. Okay, let me move this up so y'all can all see it. Okay, so now what we're going to do is see how we would come up with that equation. And so we'd have, let me just rewrite this, dy over dx equals negative x over y. Okay, you've done this probably 100 times this year. You've just never done it for this. But the first thing we always do on these, okay, is to separate the variables. All right, so that means y is on the left, x is on the right. All right, so this y that's in the denominator, I can just multiply it over to the right side, and I can multiply the dx, or sorry, dy to the left, dx to the right. What I'm writing is what I meant to say. Okay, and that part's going to change. We normally don't even have a y. Normally when we get ready to integrate, we're just integrating dy, therefore we just have y equals. Well, this is a little bit more complicated, but it's not that hard. What's the antiderivative of y? Yeah, 1/2 y squared. Now, we would write a plus c here, but what we're going to do, just like always, is we're going to write the plus c on the right side. Remember, the plus c just represents some constant, and it's going to change in the problem, so that the fact that I'm combining 2 is no big deal. What's the antiderivative of negative x? Negative half x squared, and then this is going to be the plus c. And you can subscript your c's. I could have done plus c sub 1, plus c sub 2, and then called this plus c sub 3. You could do that, but we're not going to do that in here.
Can you subscript with the letters?
You can subscript however you want. We're not going to do that. Anytime we have plus c, it's just going to be known that that means some number that I find out later. At the end, I'll find it out. Okay, so there's 2 ways we could do this equation from here. Okay, one way is to make it look like the equation I had before. What I would do then is I would add over 1/2 x squared plus 1/2 y squared equals c. And then I would multiply everything by 2, both sides. So I would have x squared plus y squared equals. Now, you might want to write 2c here. But remember, c is just some number. If you multiply it by 2, now it's just some other number. I'm still going to write c. It changed values, but it's still just representing some unknown number. It's not like we'll solve for it here in just a minute. It's more confusing if you try to do 2c here. So if I wanted to now use my initial condition, I would do 0 squared plus 1 squared. This is just like what we did before. So c would equal 1. And then, sorry, make this just a little bit. So then that would give me my x squared plus y squared equals 1. All right, now on some of these, they're going to have something like, it's going to say like y equals. This is they want you to get y by itself. All right, and so how would we here get y by itself? I'm going to go ahead and multiply everything by 2 again.
Yeah.
Just to get that out of the way. Square root both sides. And when you square root both sides, you actually have a plus minus. And what this will represent is the plus square root will be the top half of the semicircle, and the negative square root will be the bottom half of the semicircle. That's why it kind of looks strange like this. And then you could definitely finish and find C, and okay, it would work out the exact same way. All right, you'd only have to do this when you see this y equals, and so I'll mention this again on another example. Okay, and that it's going to ask for that most of the time. On this problem, it didn't really matter because we're not used to seeing circles this way. We're used to seeing them like x squared plus y squared. Okay, let's go ahead and move on to the next. Actually, I want you to skip the next page and go straight to where it says 2004 AB5 Form B. And it's like this. Okay, so here we have this differential equation. And again, this is representing all the slopes. So we're going to go ahead and do a table. And we're going to look for patterns. If there's no patterns, we just got to plug in all the points. Okay, does anybody think they see something that's like real predictable? What do you think? If x equals 0, it doesn't even matter what y equals, the slope will be 0. Okay, so we're going to go ahead and do that. Okay, what else? I did mark the origin. In this case, the only reason I didn't do it last time is because we got 0 over 0, which isn't the same as, it's not vertical or horizontal, it's its own category. Here we're not going to get 0 over 0. That's why I did mark it this time. What about a special y value? What y value pops out to you? 2. Because if y equals 2, then again, the whole thing equals 0, right? Does not matter what x is. X can be anything. If y is 2, the slope is 0 for the same reason. And all I'm doing here is just saving time. If you don't see this, then you just have to do more calculations. Okay, so y equals 0, y equals 1, y equals 2. These should also have horizontal lines. Okay, so you may or may not know any other patterns. I don't think any other ones are obvious, so I'm just going to go ahead and try 1, 0. I'll just start down here. So that's 1 to the 4th times 0 minus 2, negative 2. And we know this is going to be a negative steep line. Okay, what about 1, 1? 1 to the 4th times 1 minus 2, negative 1. So a negative, not steep, not flat, but still negative. 1, 2, we already knew. What about 1, 3? Yeah, 1. Positive 1. Okay. Yeah, you can kind of start to see the shape. It's bending. There might be asymptotes here. What if I plug in a negative x? It's the exact same as if I were to plug in a positive x in this problem. because if I take something to the fourth power, if it was negative, it doesn't even matter. So what this means is, you can kind of think of it like that. All right? The negative one is going to have the same slope as the positive one. So anytime you see something that looks like a line, that's a pretty good indicator you're going to have an asymptote. So I can see, but I also, it's still strange because I still have this going on. And so it's, maybe there's some kind of bend here. It's hard to see exactly. If we had more points, it would be a little bit more obvious. And if you're really curious, you could type this into your calculator and see the full slope field. Okay? All right, and so B is interesting because B asks a question. It says, really, the slope field is everywhere. We only drew part of it. But can you look at part of it and make a conclusion for everything? So what we want to know is, where are the slopes negative? Okay, so they're negative here and here, but not up here. So in words, we could say below the line y equals 2, but we have to say not here, not when x equals 0. Let me show you algebraically how this happens, because again, it's not obvious. Some of you are going to really latch on to the visual, and some of you are going to really want the algebra. So I just need to solve this. Okay, x to the fourth, always positive, right?
Yep.
But x can't be 0. I gotta state that. Okay, but other than that, I don't even have to deal with it. If x is 0, I'm not negative, I'm 0. And so if I were to solve this, then I would say y is less than 2. And so the points in the xy plane where the slopes are negative fit these conditions right here. And there's a variety of ways you could say that, but it would need this information. I'm going to go ahead and move on to the next part because I want to have full time to talk about this. So C says, find the particular solution, y equals, okay, we see the y equals. This means we're going to have to get y by itself. That's your clue. It says, given differential equation with the initial condition, and this is how we're going to find C, just like how we did before. All right, and so if I look back up here, I see x to the fourth, y minus 2. So let's rewrite that. dy over dx equals x to the fourth, y minus 2. And I need to separate the variables. So how am I going to get the y minus 2 over to the left? Divide. So watch what I'm going to do. 1 over y minus 2 dy. It could be dy over this, but we're just used to seeing it this way. So it's going to be easier for you. It's just the same way you're used to seeing it. Okay, on the right side, I have x to the fourth, and then multiply the dx. You have to get y's and x's separated before you do the integration. We have never integrated x and y together. We've never done that. We only integrate x's or y's or u's or t's, but never when they're mixed. Okay, so now we're going to integrate both sides. What's going on over here?
U substitution.
U substitution. Okay, so we're going to need to do that. U equals y minus 2. That's going to make du equal dy. That's going to make that 1 over u du. And what is the antiderivative of 1 over u du?
Natural log, absolute value.
Natural log of absolute value of u. Okay, so all of that to say, I'm going to switch color here. This right here is going to become natural log of y minus 2. And again, the plus c, we're just going to put at the very end on the right side. Okay, antiderivative of x to the fourth. Yeah. However you want to write it, it doesn't matter. And then here's where we put our plus c's. Okay, let me move this real quick. Okay, be by itself. That's what they told us in the directions. That's what we need to read into that. But it's locked inside of a log. How do you open up a logarithm? Yeah, we're going to have to think, okay, this really is base e, log base e, and I need to rewrite this as an exponential equation. Okay, so this y minus 2 then is going to equal e to the power of everything over here. All of this is in the power. This is where we're going to use what we know about logarithms to help us out. And this part will get easier because it kind of works very similarly on the problems we're going to see after this. This happens a lot. When your y is inside a log, you're going to have to rewrite it as e to some power. Okay? Before I add over the 2, I want to consider this. Okay? This plus c is part of the exponent. Watch what I'm going to do here. Yeah. I'm going to do that. Now, probably you would never think to do it. Maybe you would. If you would, good job. That's clever. But most of you would not think to do this, and that's okay. I'm telling you, this is where we're going to go. I need to get that c out of the power. All right? And so, and I can do this, if you think about it, x squared times x cubed, wouldn't you just add the powers? So what I did is I just broke it apart. All right, now, e, which is a number, raised to the power of some number, is just some other number, correct? So I'm going to replace that with just regular c. It's a different c. Okay, c is changing. It's fluid. Here it was some number, here it's some other number, but it's still just a number. And we're not going to find c until I can still get y by itself.
So we got the 2, it's just...
Yeah, so I'm going to go ahead and move the c to be in front of this e, by the way, because this is how we're going to see it. No pun intended with that. I really, truly not mean to make a pun with that.
Folks, couldn't you have just done that to begin with?
What do you mean to begin
Just
with?
move to the C to the...
Do you mean from up here?
Yeah.
Yes, and now you know, hey, when plus c is in the exponent of e, it's going to become an exponent. This is not a log property, though, which is what you might be thinking, but it is going to work this way, only with c. It would not work this way with a variable. It wouldn't work this way with any other number. It only works this way with c because we can change c, and as long as we know it's just some number, we can just keep writing c. And if this is, if this is like just gets under your skin, then write a subscript and just say, okay, it's still a constant, but it's some other number.
Shouldn't the 2 be incorporated into the c in the last equation?
What do you mean?
Like it's a constant as well.
Yeah, but it's not multiplied to this.
Oh, okay. Okay, so just...
Or like this thing is not like plus c, it's times c. That's the difference. But you're right. That would change that. Okay. All right, this is getting choppy here. Almost quitting time. All right, so here's what I want to ask you. Let's box this. We're almost done. But does this CE to some power look familiar at all to you? Have you ever seen this equation? Don't write this down. I'm about to erase it. Whoops. Have you ever seen this?
Oh,
Or
yeah.
have you ever
It's in the
ever seen this?
money problems with the...
Half-lives,
Yeah.
bacteria, money in the bank, all of this is this format. That's why I wrote it that way. That's why I made it a big deal that we got C in front. We're going to talk more about that tomorrow. Okay, so the only thing I need to do now is I need to find C. So we're going to use our initial condition. We're going to say, okay, when x is 0 and y is 0, all right? And so this is almost always like really easy to calculate. The reason is because look what happens when you let x be 0. That whole thing becomes 0. And e to the 0 is 1. not 0, 1. So 0 equals c plus 2. That means c is going to equal -2. So my final answer is -2 e to the power of 1/5 x 5th plus 2. And I can't use log properties in this right here. Okay, this isn't a log, this is an e. Okay, so actually